I'd now like to go through a few examples of some basic momentum problems that you will be expected to encounter and how to handle them. There's some striking similarities in how to deal with any given momentum problem, and then we just have to fine-tune it as we go. So in the first example, we have a 4-kilogram block and a fairly large bullet's going to embed itself in, moving at 50 meters per second, into the block, which is at rest. So it merges with the block and the whole system moves on afterwards at what speed? Which is the question. What speed does it move on at? So object 1 is M1, that's the bullet. So this is object 1, this is object 2. We start with the basic idea that total momentum is conserved, so momentum total before is total momentum after with the prime notation. So we're going to expand that out. What's the total momentum before? Remember, definition momentum is mass times velocity. So it's the mass times velocity of object 1 and then plus object 2. So here it is, m1v1 plus m2v2. The bullet's original momentum, the block's original momentum. And that's going to be what they are afterwards, because afterwards it's the same thing. Now, a lot of times this can be simplified, and in this case, definitely. Because what's the velocity of block 2 originally? Yes, it's 0. It's not moving. So that's 0. Moreover, there's another simplification. What's the relationship between the velocity of the bullet and the block after they've embedded into each other? You guessed it, they're the same. Since they're the same, why have a 1 and 2 subscript? Let's drop the subscript and call it the velocity after. And then we can just say m1 plus m2 quantity times the new velocity. So there we go. What are we trying to solve? We're trying to solve for this. So this whole thing equals m1 v1. So let's do it. v prime m1 v1 over m1 plus m2. Plug in the numbers. 0.3 times 50. It's the original momentum of the whole thing. Right in there, divided by the addition of the masses is all it is, which might seem a little bit intuitive, perhaps. And there's the answer, folks. Okay, that was an inelastic collision. Now let's do an elastic collision. So we've got the conditions here. We've got 2 carts, one at rest, one moving at 10 meters per second, a 3-kilogram cart, so hitting a heavier cart. This is the before scenario. Then there's a collision. Collision happens, and after that, the 3-kilogram is moving at some speed to the left, while the 5-kilogram is moving at 7.5 meters per second to the right. And our objective is to figure out just how fast this 3-kilogram cart is moving. So we're going to start with the total momentum before and after being the same. And so we write that out in detail with a 2-body situation again, m1 and m2, along with their respective velocities. And we get what they are afterwards. So same thing, same way we started before. Now what's different? Well, one thing that's the same, this is not moving, so this is 0. Okay? But in the inelastic case, these two velocities were the same, so we could combine them together. No longer. There are 2 different velocities. In fact, it's this that we're looking for, v1 prime. So let's just go ahead and solve it algebraically right now. That part's easy. So we subtracted this from this side. So m1 v1 minus m2 v2 prime over m1. And I think we have all the data. So 3 times 10, the plus and minus signs are real important now, minus m2 v2 prime. It's going in the positive direction. Over 3, and out pops minus 2.5 meters per second. So there's our answer. The negative shows up, and it in fact indicates the relative direction, being opposite of our chosen positive direction. Now, this would be a little more complicated if this was not known. If we just had this collision, and we didn't know what this was, but we could figure it out. We just need another equation, though. We would need conservation of energy because we have 2 equations and 2 unknowns. So, I mean, we have 2 unknowns, v1 prime and v2 prime. We couldn't solve it with just this equation, but with energy we can. Now, we haven't studied energy yet, but there's an interesting relationship that pops out of the bringing together both of these conditions, and that's as follows. That the initial velocity of object 1 plus its final velocity equals the initial velocity of object 2 plus its final velocity. Okay, so that kind of rolled. Well, we can rearrange this and say v1 minus v2 equals v2 prime minus v1 prime. So this is the velocities before of the two objects. This is the velocities after. Now I'll just take this a little further. This is minus v1 prime minus v2 prime. So v1 minus v2 equals negative v1 prime minus v2 prime. What does that mean? The relative velocity of two objects in an elastic collision basically switch places, equal and opposite, no matter what the mass is. Let me state it in a different way. This is an expression of the relative velocity of objects 1 and 2. Okay, as these carts combine, this is the relative velocity as they come toward each other. After the interaction and they're separating, this is the relative velocity of the carts after the interaction. And there's a negative in front of it. So the relative velocity before and the relative velocity after. After is just the negative of the first, which in a practical sense means the following. If you were watching this collision, the rate at which this gap closes, the rate at which it closes is the rate at which this gap opens. I'm not sure which way to make my laser beam go because they're both moving apart. But the gap opens at the same rate that this gap closes. Any combination of masses on either cart will result in that very interesting reality. And now let's consider an explosion. The cannon of physics, firing a 1 kilogram cannonball at 300 meters per second, kicking this, well, unfortunately, tiny cannon back, and we're going to figure out how fast it's moving backwards. Here's the data, the masses, the initial velocities. And so we have total momentum is conserved, or changes in momentum are equal and opposite, both of which are going to be seen to be applicable here. So starting with total momentum before equals total momentum after. Same thing I wrote before. Now, what factors here disappear? Well, originally, the cannon is sitting there with the cannonball in it. They're both not moving. So M1V1 is gone, and M2V2 is likewise gone. Therefore, we simply have, looking at this, that M1V1 prime equals minus M2V2 prime, which is seen to be an expression of the change in momentum of object 1, namely the cannon, is the negative of the change in momentum of object 2. How do I know these are the changes? Because their velocities started at 0, and this is what they're ending up being. Okay, so that is the change. So total and change both makes sense here. Now, just solve for V1 prime is what we're looking for. And the numbers come out real easy. 1 kilogram, 300 meters per second over 20. Minus 15 meters per second, indicating the cannon is moving in the negative direction. So that's how to analyze an explosion. And now let's do one more, an impulse problem, where we have a 2 kilogram bowling ball is dropped and lands at 5 meters per second, bounces back at 4 meters per second. Right away you'll notice it has different momentum when it hits than when it launches back up, which is perfectly valid for a given object, as long as the system doesn't change in momentum. I'll leave that alone for the moment. You might want to think about, though, what is the rest of the system? But at the moment, we're just concerned about this one object. It bounces in 1/10 of a second. Determine the impulse imparted to the ball. Now, if you give an object an impulse, that means its momentum is going to change, because that object gets a net force times a time, or its mass has a change in velocity. both of which mean impulse. Impulse or change in momentum. Then we're going to figure out the average force the ball experiences.
Basic concept.
So impulse is change in momentum. Well, let's just go ahead and go with that. The change in momentum is m delta v, and the v's are in different directions. So in one direction it's 5, the other direction it's 4. So that's mass times final minus initial. The final is 4, and I'm going to call that positive. So this is 2 times 4 minus, the 5 is in the negative direction, so negative 5. And that's equal to 18 Newton seconds. It's a big difference. If you would have called that 1, if you would have said 2 times 1, that'd be really ridiculous, or negative 1. Very incorrect. It's easier to stop the ball to a dead stop than to launch it back the other direction as well. It requires a greater impulse to bounce off.
Basic concept.
And so now impulse is F delta T. From this we can find the force. We already know the impulse. It's 18. The time is 0.1. 180 newtons is the answer we're looking for. Okay, to finish off this video, I'd just like to consider the idea of the center of mass of an object. Let's choose the canon of physics. Perhaps a little gratuitous here with the sounds and the animation, but nevertheless, we have a cannon projectile being launched and then it explodes in midair. So it's an explosive cannonball. And what I want to do is plot the center mass. The center of mass. We know gravity, if it all stays in a ball, gravity takes it down, so that's the plot to that center mass. But what about when all the pieces are flying in every direction? Well, later on, here's the center of mass. And I'm trying to indicate the velocities of the particles here by these arrows. And so a little bit later, there is the position of those particles. But when you add them all together, when you take the mass-weighted average position of all those particles, you get that same center mass right there, where it would be if it hadn't exploded at all. Okay, so that I had alluded to before, so I hope this makes it more clear, that actually the center mass would plot as though the explosion had never happened at all. The explosion is an internal phenomena, internal to the object in question, namely the cannonball. So it can't change its own momentum unless there's an external force acting, and there isn't any. It's all internal explosive action-reaction forces. So it's the same parabolic path it would have if it hadn't exploded.